Good morning, students. Am I audible?
Good morning, sir.
Good morning. Just wait 2 minutes, then we will start the session. Okay.
Yes, sir.
Just wait 2 minutes, then we will start the session.
सर आज लैब होगा या सर थ्योरेटिकल क्लास होगा?
Theoretical class hoga. There is a problem in the lab. That's why today we will take the theory class, and after the schedule, I will inform you the lab session. Okay.
ओके ओके सर.
Okay. Now let's start the session. Actually, in the last class, we have studied the multiplexer, and today we will study the demultiplexer concept. Okay, demultiplexer or the data distributor. Okay, and yes, I know that actually this time is for the lab session, but there is some problem in the uh, class, in the lab class. That's why I am continuing here the theory class today. Okay, one thing. So first we will discuss, that is the demultiplexer. And one thing, yesterday class I also informed that in a Google Classroom I will create a assignment link, and I already given you some assignment so yesterday. So after this class you will get the link, and you can submit your assignment copy in that particular link. Okay, So demultiplexer, actually this means that one into many. So in the last class in Marx concept, we have seen there is n number of input as well as only one output, and there is 2 to the power m concept of select line or control line. So here we will see in the process of demultiplexing only one input and many output. This is the main difference of Marx and Demarx. Now, demultiplexing is the process of taking the information from one input and it is transmitting the same data to the one over one of several output. That's why for the case of demultiplexer, there is one input and n number of output. Okay, and this demultiplexer as is a logic circuit actually, and that receive the information on a single input and transmit the same information over one of several to the power m output lines. So if I draw here the block diagram of demultiplexer, so this is one input and here n number of output signals, and as well as here also the m select lines. So this is Demarx. Here actually, so from this block diagram you can see this is the opposite of a multiplexer and the operation is again the opposite here, and here the circuit has only one input. This is a one input and m select line, this is selector line at the control lines and the n output signals, and here the select input determines that to which output the data input will be connected. So as the serial data is changed to parallel data, so the input cost to appear on one of the n output lines. So demultiplexer then called that the serial to parallel converter. Okay, so first I will draw here the 1:4 marks. In the last class we have discussed that is 1:4 Demarx. So in the last class we have seen the 4:1 marks. So for the case of 1:4 Demarx, this is actually you can say 1:4 Demarx logic diagram. So here this is the 1 and this is the 4 output signal. But if the 4 output signal is there, so how many select line should be there?
2, sir.
2. Very good. So okay, suppose this is S1 and this is S0. Okay, and here suppose this is Y3, Y2, sorry, Y3, Y2, Y1 and Y0. Okay, so Now I will draw the truth table of 1:4 demarcs. So the truth table. So first here, input data, data input. This is the select line. Select input, you can say. And this is the output. So all the cases here, suppose there are 4 combination. So first one here, suppose it is data input is D. Here I am denoting, and this is S1 and S0. The 2 select lines, and the 4 output Y3, Y2, Y1, and Y0. These are the 4 output here. And suppose all the cases the data input is D, 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 and D. And here this is 0, 0, 0, 1, 1, 0, and 1, 1, because we have 2 select line, and from this 2 select line there is 4 combination, that is 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so now for this case for this case the output is here, that is only 0, 0, 0, and D. In the second case, that is 0, 0, D, 0. Third one, that is 0, D, 0, 0. And the fourth one, this is D, 0, 0, 0. Okay, so from this truth table, that is the 1:4 demarcs, that it is clear that the data input is connected to the output, that is Y0, when only S0 and S1 both are 0, and the data input is connected to output Y1 when the S0 is 1 and S1 is 0. Similarly, the data input is connected to output Y2 and Y3 when the S1 equals to 1 and S0 equals to 0, as well as when S1 equals to 1 and S0 equals to 0 here respectively. Okay, so from this truth table, actually the expression for the output we can be written like that, that is the suppose here y0 equals to, that is S1 bar, S0 bar, D. For the case of Y1, S1 bar, S0, D. For Y2, it is S1, S0 bar, D. And for Y3, it is S1, S0, D. Okay, so these are the outputs. So this output we are getting from the truth table. Okay, so now using the above expression here, we can easily implement, that is 1 to 4 demarcs. So to implement the 1 to 4 demarcs, we need so first here I am erases these things to draw the logic diagram. Okay, so now we will draw the logic diagram of 1:4 DMARCs. Okay, so for this, the first one is for the data input, that is D, and the second, and this one is the select line. And you just saw from the expression there is a bar and unbar terms, so we need the NOT gate also for the bar to get the bar terms. Okay. So first y0, for the expression of y0, it is s1 bar, s0 bar, and d. So from this is d, s1 bar and s0 bar. Second one, suppose this is second expression, that is s1 bar, s0 d. So this is for y1. Third one, that is s1 s0 bar d. The fourth one, that is y3 for s1 s0 d. Okay. So you also know, for the whenever there is expression in multiplication, so multiplication means we need the AND gate. So here we are using the AND gates. So to implement the 1:4 DMARCs, actually we need two NOT gate and 3 input AND gates, 3 inputs AND gates. So with these 2 gates we can easily implement the 1:4 DMARCs. Okay, and here you can see the input data line is connected to all the AND gates, and the 2 select lines, that is S0 and the S1, is enable only one gate at a time, and the data that appears on the input line passes through the select line to the associate output line. This is the concept about the 1:4 demultiplexer. This is the logic diagram of 1:4 DMARCs. Okay. So is there any doubt for 1:4 DMARCs? Is there any doubt? No response. Okay. So now I am requesting all the participants write your name in the chat box for the attendance. I am giving you 1 minute for the attendance. Okay. So yes, I got the all attendance here. Okay. Now the next is just 1:8 DMARC. Okay. So just give me 1 second to share the screen. I think the screen is visible for all of you. It is visible, yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So this is the 1:8 DMARCs. Okay. So the first one you can see, this is the logic symbol, and the right hand figure is the logic diagram of 1:8 DMARCs. Okay. So here for the case of 1:8 DMARCs, you can see here there is a single input, that is D, the data input, and the 8 outputs, and 8 outputs from it is Y0 to Y7, and the 3 select line. So 3 select line, there is 8 inputs. So based on the output lines, we can see here the 3 select line and the control line, that is S0, S1 and S2. And here you can see that it distributed the 1 input line to 8 output line based on the select line. And the truth table, I am here not drawing the truth table actually. So you can easily from this the previous one. So from the previous one, we got the Y0, Y1, Y2, like from Y0 to Y7. Okay. And based on the expression, um, we 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 can easily implement here the logic diagram of 1:8 demultiplexer. And here you can see this is the diagram for 1:8 demultiplexer. Is there any problem to understand 1:8 demultiplexer? In the last class, I have said that for your assignment, you will submit that is the 8:1 multiplexer as well as 16:1 multiplexer, the truth table, logic symbol as well as the logic diagram for both cases. Now I am adding another topic, that is the demultiplexer. From demultiplexer you will do the 1:16 demultiplexer, and for this 1:16 demultiplexer you will draw the logic symbol of 1:16 demultiplexer, as well as you will write the truth table and the logic symbol. Okay, and I will create the link in the Google Classroom today, and I will mention here all the details. Okay, so now one thing here actually, I am here mentioning the IC number of all this demultiplexer. Okay, so this is 74139 and 74155. This is the dual 124 DMarks, and this is also dual 124 DMarks, and 74156 also same. Okay, next is 74138. This is 128 DMarks, and this is 74154. This is 1 to 16 DMarks, as well as 74159 also the same. Okay, this is for this is also called 224 decoder. This is 224 decoder, and this is 328 decoder, and this is 4 to 60 line decoder. Sorry. Okay, so next topic that we will discuss here, that is the decoder. What is decoder? Decoder and encoder. Just 1 minute. Okay, so what is decoder? A decoder is similar to the demultiplexer, but there is a difference. What is the difference? In demultiplexer, we have seen there is one input and n number of output, but in decoder there is no data input, there is no data input. Okay, and most of the digital system requires the decoding of data, and decoding actually is necessary in applications such that demultiplexing, digital to analog converter, memory addressing. This is the area, the application where the decoder is used. And here actually decoder is a logic circuit that actually converts an n-bit binary input code or data into 2 to the power n output lines, and such a way that the each output line will be achieved for only one of the possible combination of input. So in a decoder, the number of output is greater than the number of input. Okay, and it is important that one thing for this case, that if the number of input and the output is equal in a digital system, then it is called the converter. So when the in the case of decoder, the number of input and the output are equal, in that sense it is called the converter. So BCD to XS3, gray to binary, these are the binary to gray code, these are the converters. Okay, so first is that the basic, that is basic binary decoder. So here that is basic binary decoder. Okay, so to implement the basic binary decoder, actually we need the AND gate. Okay, mainly AND gate. So with the help of AND gate can be used as a basic decoding element. Because why it is used as a basic decoding element? Because its output is high when all the inputs are high. When we are giving all the inputs 1, so we are getting output also in the case of output 1. So for the example, if we consider the binary number, if we consider suppose a binary number that is 1001. So then to make all the inputs to the AND gate high, the middle bits, that is 0, must be inverted by using 2 NOT gate. So the here I am drawing the figure. Suppose this is A, B, C, and D. So this is one, 0, 0, 1. So this is 0, 0. So in the NOT gate, when we are using the NOT gate, so output here it should be 1 and 1. So here y equals to D, C bar, B bar, and A bar. So if the NOT gate is used in place of AND gate, then the low output is generated to indicate the presence of the proper binary code. Okay, actually the basic binary decoder is I think is not in your syllabus. In your syllabus, that is 3 to 8 decoder and 4 to 16 decoder. Okay, so the time is almost okay over. Okay, let's for the 3:8 decoder, 3:8 decoder. So 3:8 decoder, from the name you can easily understand that there is 3 input and 8 output, and based on the 3 input, one of the 8 output is selected. So the truth table, I am here, the truth table, okay, I am here writing. Suppose this is the input and this is the output. Suppose this is A, B, and C, and this is D0 to D7. Okay. So there is 8 combination, 0, 0, 0. Okay, so you should write like that: 1, rest of the part 0. This is 0. You can easily write here like that. Diagonally, it should be 1. 1. This is the, yeah. So this is the truth table for 3:8 decoder, and from the truth table that you can easily understand that only one of the 8 outputs is selected based on the 3 input line, and also from the truth table the logic expression for the output also can be written here. So for the case of D0, for the case of D0, the output is A bar, B bar, and C bar. For the case of D1, output is A bar, B bar, C. For the case of, just 1 minute. For the case of D1, it is A bar, B bar, C. For the case of D2, it is A bar. You just look into this output, sorry, input. So here D2, it is A bar, B, C bar, D3, A bar, B, C, D4, A, B bar, C bar, D5, A, B bar, C, D6, A, B bar, C bar, sorry, A, B, C bar, D7, A, B, C. Okay, so from this expression you can easily draw the logic diagram for the 3:8 decoder. So for the 3:8 decoders, we actually needed the 3 input AND gates and the NOT gate. So with the help of 3 input AND gates and NOT gate, we can